Hello and welcome everybody to our webinar of 30 minutes about innovative perspectives with CHNS analysis for green material research. Today we will present a success stories from the University of Messina with a special guest and speaker. I would like to introduce you the agenda. So first we will have an introduction to elemental analysis, then sample preparation, a chapter about the principle of operation of our elemental analyzer, and then the case of University of Messina. As a final chapter, we will have the question and answer section, and we would like to ask you, if you have some question, to write them on our chat form that you will find on the right part of this webinar. The presenters of today will be myself, Martina Casonato, that I'm the Development Marketing Manager, and Viviana Bressi, as a postdoctoral researcher from University of Messina. So let's start our webinar with the introduction to elemental analysis. Just for refreshing our mind, what is elemental analysis? The primary application of elemental analysis is in organic elemental analysis, which quantifies the carbon, the hydrogen, the nitrogen, the sulfur, and even the oxygen of organic compounds. The combustion analysis is the gold standard for determining the CHNS content in organic compounds. In this method, a sample is combusted in a high temperature, oxygen-rich environment, breaking it down into its elemental gases like CO2, H2O, the N2SO2. These gases are then measured using detectors, and then elemental composition is calculated, as shown here in this slide. The combustion analysis is widely used in industries such as food and beverage, petrochemical, environmental agriculture, pharmaceutical, and material science, thanks to its precision and reliability. In this case, we will present a success stories about material science. In our portfolio, we can find 3 different elemental analyzers, but today our main guest will be the EMA 502. That is valve all-in-one solution for the determination of carbon, hydrogen, nitrogen, sulfur, and oxygen. The CN802 for the determination of carbon and nitrogen, and the NDA 702 for the analysis of nitrogen and protein following the Dumas combustion method. But which are the main features of EMA 502? First of all, it's an all-in-one compact solution for the determination of CHNS and the determination of oxygen. Another great feature of our elemental analyzer is the accuracy and the reproducibility. So the gas chromatography column ensures a complete separation of all the elements that are detected by our TCD. It's a simple and flexible solution, so a routine of solids, liquids, and matrix independence results are easily calculated, and we have a very simple maintenance. We have double gas carrier choice, and that you can utilize argon instead of helium as a carrier gas in order to reduce the cost per sample. It's an easy to use solution. So with our software, EMAsoft, is a user-friendly interface that provides comprehensive information at a glance for your data. Last but not least, we have the cloud connectivity, so you can streamline your routine operation with the real-time monitoring of your data anytime and anywhere. Okay, let's move forward to the sample preparation. The sample preparation requires, of course, some care and attention since very small quantities are used. Solid samples should be ground to fineness of 0.5 millimeters to obtain an homogeneous sample. The degree of homogeneity of the sample is one of the most important factors which affects the quality of the analysis results. Moreover, it's important to mention that when weighting milligrams of sample, a microbalance is highly recommended because the balance can influence the measuring of the accuracy. Regarding the sample preparation of solids is very easy. So we need just to add the sample into a tin foil, close the tin foil over the sample with the aid of a tweezer if needed, and put it into the autosampler. One disk is for 30 samples, and since our autosamplers are stackable, you can collect more than 170 samples with just 3 disks. The correct sample weight depends on the analyte, so like the N, the C, the H, the S, the O content of the sample to be determined. In microanalysis, the sample weight should be between 2 and 5 milligrams in most cases. But higher is the amount of carbon in the sample, lower is the weight. On the other side, in some soil with carbon content, for example, lower than 1%, it's possible to reach 90 milligrams of sample, but just in case of carbon content lower than 1%. In the combustion zone, the oxidation of the wrapping material generates a short time temperature of 1800 degrees Celsius, and it's so-called the flash combustion. While for liquid sample preparation, we have 3 different methods because can be presented several and difficult challenges to be handled. The first method indeed employs the VELP super absorbent powder to soak up the liquid and solidify the sample for easy encapsulation within a tin foil. The second method for laboratories handling larger volumes of liquid sample, VELP can offer thin capsules with dedicated disc for capsules. While the third method is for analysis requiring high sensitivity compared to the previous methods. So there is a direct injection into the combustion area directly with a syringe. If you so required high accuracy and precision, this is the method of your choice. So now let's move on to the principle of operation of our EMA 502. So this is the flow diagram for the determination of the CHNS. The sample is transferred to a purge chamber in the autosampler where a flow of helium or argon purges nitrogen before entering in the combustion chamber. The sample drops down the combustion tube at a temperature of around of more than 1000 in excess of pure oxygen for the conversion into the elemental compounds. In the top of our furnace, during the combustion, the elemental components of the sample are quantitatively converted into gaseous oxidation products, while in the bottom, the formulation of active copper powder placed in the lower part of the combustion reactor completes the process by reducing the nitrogen oxides, NOx, into the molecular N2. And then we will have the formation of our reference gases. Then the gas stream reach the gas chromatography column, which ensure the homogeneous and complete separation of all the elements prior to the final detection by the innovative TCD detector. The analysis is more or less about 12 minutes, so it's a fast determination of all these 4 elements. Now we'll have a close-up of what we have here in the monitor of our laptop, the determination through the real-time graph with the EMAsoft with the peaks for the complete CHNS determination. The reactor for the CHNS is just one reactor to perform combustion and reduction in one single step. We also have a solution for the pre-pack reactor, so you don't have to prepare it by yourself. We have different components of our reactor, and you can also use a quartz ash collector that is suggested for soil and ash-rich samples, while it's not needed for organic samples. So switching from CHNS to oxygen mode is really easy. It's not required to add any additional external modus, and you can easily change the mode into 3 easy steps. So change the reactor, change the connection panel, and then change the GSE column. The instrument is ready to work in a very few minutes. So as mentioned before, the EMA 502 is a all-in-one compact solution. So now let's see how the determination of oxygen is working with the flow diagram of our elemental analyzer. The principle of operation is similar to the classic CHNS mode, with the difference that for the oxygen determination, we have to work without oxygen, that is called pyrolysis. In this case, the sample is transferred to a purge chamber in the autosampler, where a flow of helium and or argon purges nitrogen before entering in the combustion chamber. During the pyrolysis, the oxygen of the sample is quantitatively converted into gaseous CO. Then through the connection panel that we have already made the change from O to the CHN from the CHNS configuration to the O, we go through the chemical trap where impurities are absorbed, and then in the gas chromatography separation where there is the separation of the CO from impurities. And after that, of course, the thermal conductivity detector detects the oxygen in just 6 minutes. The reactor for oxygen is made for the pyrolysis mode, and so the samples are heated in a high temperature furnace, around more than 100 of degree, without the presence of oxygen, as mentioned before. Also in this case, we have a pre-packed reactor, and the use of ash collector is highly recommended for sample of soil and ash-rich samples. Of course, for organic sample is not needed. Now I will leave the word to Viviana Bressi, the postdoctoral researcher from University of Messina, that will highlight the innovative perspectives with the CHNS analysis conducted with our EMA 502.
Okay, many thanks, Martina, for your kind presentation, and thanks to VELP to give me this opportunity to talk about our project in which we are involved. I'm Viviana Bressi, postdoctoral researcher at the University Mediterranea of Reggio Calabria, but still in collaboration with the University of Messina, in which I spent more than 8 years between master and PhD studies. And today I'm going to talk about our project and how the elemental analysis improved the quality of our materials characterization. Before to start to talk about the work, I would like to present our chemistry lab in the University of Messina within the engineering department. Our lab is home to a dynamic team of collaborators from all around the world, including physics, chemists, engineers, pharmacists, so bringing together a different range of skills and expertise. About our project, the goal of all of them in which we are involved is innovation, so try to improve and to study and to perform innovative technologies. And the first and primary goal is sustainability. It's not so simple in a chemistry lab to follow all the 12 green principles, the principle of green chemistry, but we are trying with all our collaborators to advance the new technologies for developing sustainable world. Before to start to talk about the characterization of our materials, we need to talk which kind of materials we are going to produce and to synthesize. Our first goal is to valorize biomass and converting biomass in high value compounds, like for example the one that you can see in this slide. The process that usually in my group we are carrying out is called hydrothermal carbonization, which is an hydrothermal conversion of the raw starting materials, so the biomass without any pretreatment is carried out in water media and is performed under mild condition. At the end of the process, we are recovering three products, the gaseous, liquid, and solid phases. Gaseous phases is mainly composed by CO2. Liquid and solid mixture is filtered and separated. So from the liquid part, we are going to extract bio oil, in which we can find really interesting chemicals. For example, starting from orange peel waste, it's possible to recover 5-hydroxymethylfurfural, which is coming from the conversion of hemicellulose. And the solid part. The solid part is called the hydrochar. Hydrochar because it's the char, so the carbon phase coming from the hydrothermal process. The hydrochar is a carbon-rich materials which can be used for several applications. First of all, usually is used like for the remediation in the soil. It could be activated, so converted into activated carbon, which can be used like adsorbent for inorganic and organic pollutants. Or in our case, we use it as a starting material for the synthesis of nanomaterials, which commonly are called carbon nanomaterials or carbon nanodots according to the dimension. And in this background, CHNS analysis was playing a crucial role in this project. Because thanks to this analysis, we were able to confirm the elemental composition of our materials. So the materials was nanomaterials derived from industrial waste. And this industrial waste was coming from brewing industry. So it was mainly composed by cellulose and protein. So thanks to the elemental analysis, we were able to confirm the presence of nitrogen because of course, carbon, the percentage of carbon is in our materials always high due to the process. But nitrogen was playing a crucial role for us also to explain the application of these carbon nanomaterials. Of course, the CHNS was also a technique to confirm what other characterization technique were able to show us. For example, the FTR, which is a technique in which it's possible to understand the functional groups of a material. And also the technique I'm reporting here, the microscope, to show the small nanoparticle with a circular shape, the Raman spectrum. These carbon nanomaterials were used and applied as fluorescent probes, and also they were applied as electrochemical sensor. First of all, the fluorescence is possible to see by this picture, how much these carbon are really fluorescent, so how much is the fluorescence intensity emission. By adding into the solution heavy metal ions, was possible to see a quenching of this emission, especially with mercury, in which high concentration was completely switched off. So following the last part of the application was to develop electrochemical sensors. We are using screen printed carbon electrode, in which we are drop casting into the working electrode our solution in order to modify and to improve the sensitivity and the selectivity of the sensor. According to the response to the heavy metal ions, it was analyzed also the capability how these carbon nanodots could improve the electrochemical behavior. So it's possible to see that we reached a really interesting goal by improving the capability of this sensor with really low limit of detection for all of these heavy metal ions analyzed. Simultaneously analyzed through square wave anodic stripping voltammetry. To conclude, some other projects in which we are involved and other collaboration with other departments and also other universities. So we are really proud about it. And I'm reporting the data obtained with the elemental analysis. So thanks to this kind of analysis, it's possible also to collaborate and to extend our world of knowledge. Okay, many thanks for your attention, and thanks again to you, Martina, and to VELP for giving me this opportunity.
Welcome back to our last session of question and answer. Thanks to all of you for writing so many questions. After this webinar, we will follow up with all of them, and we will answer through email. Since the time is running, we will just pick up a few questions, like the one that just arrived a few minutes ago is how long does the pre-packed reactor last before it needs to be replaced with a fresh one? Of course, depending on the sample, but average, you can consider 250 analyses for a pre-packed reactor, and then should be replaced. The second one is, can we do inorganic sample analysis? No, our elemental analyzers are specifically designed for organic sample analysis only. So you cannot conduct any inorganic sample analysis. Which gases are required to start up the analysis? Helium or argon as a carrier gas with the purity of 99.999%, grade 5.0, and the oxygen with a purity of 99.999% with a grade of 5.0 for the combustion. With argon, it's only possible to detect the elements CHN and it has a lower sensibility, but you can save some costs for running analysis. I would like to thank you, all of you, for participating at this webinar, and a special thanks to our main speaker and special guest, Viviana Bressi, for her participation. Thank you very much.